Morning everyone, welcome to today's GCSE Physics live group tutorial. Thank you for joining us, hope you all had a nice evening. Today's topic, as you know, is forces recap and some work on exam techniques, so should be a really helpful one today. Welcome back, lots of you have joined us for these sessions before, and welcome if you're new. This will be a 1 hour session as usual, so we'll finish at 10:15, and if you have any questions throughout, just pop those in the chat or the Q&A. Our tutor will keep an eye on those, as will I, and we'll have a time for some Q&A at the end. So any questions you have about the online school or about the content that our tutor's going through, just let us know and we'll keep an eye on that. Our tutor today is Preshayla, who's our physics tutor, who lots of you know and have had sessions with before. She studies physics at Loughborough University, and this is her 4th year as a tutor. So what we'll be going over today, as I said, is a recap of the forces topic. So that's a recap of all forces, then sort of around 15 minutes for exam technique work, and then as usual, time for questions at the end. Are you all good to go, Preshayla?
Yeah, all good.
Brilliant, have a good session.
Okay, so yeah, we're going to be going through all of forces again, so don't worry if you've missed the webinar and haven't had time to kind of catch up, and also don't worry if you can't remember back to last week. We're going to go through it all again. So first of all, we looked at forces and elasticity, and we looked at change of shape and how an object can change shape. So it can either bend, which is this one over here, compress, which is squishing together, or stretch, which is this one here. But to do so, it requires more than one force. So we can't compress an object just by pushing it on one side. It needs to have 2 forces. And we talked about change of shape. It's kind of special word, which is deformation or deformation. So it's a key kind of term that you need to know, and it basically just means changing shape. So it doesn't mean like damaged or defect, it just means changed in shape. Now there's 2 types of deformation. There's elastic and inelastic. So elastic deformation means that it can return to its original shape. So when you stretch it, bend it, compress it, it will return to its original shape. So it's not a permanent deformation, it's a temporary one, and then when you release the force, it will return. So an example of this would be a rubber band. And then inelastic deformation is when we permanently deform something, so it can't go back to its original shape. It's a permanent change. So for example, a tin can, if you were to crush a tin can, it would be permanently deformed and you would never be able to get it back to its original shape. Okay. So then we went on to talk about Hooke's law, which is this idea that extension of an object is proportional to the force which we apply to create that extension, provided that we don't pass the limit of proportionality. So it was this equation that helped us to understand it, which is force equals spring constant times extension, where force is measured in newtons, spring constant K is measured in newtons per meter, and extension is just a distance, so it's measured in meters. So spring constant is this idea of how hard it is to stretch. So for a rubber band, it would have a very low spring constant because it's very, very easy for us to stretch. Okay. However, a wire would have a very, very high spring constant because it's really hard for us to stretch it apart. So that's what spring constant means, and it's constant for a single material. So for example, a rubber band has its own spring constant. A wire has a different spring constant. So the spring constant never changes for material. Therefore, we call it a constant. Okay, so a constant, it never changes for that material. Then we looked at the graph. So the graph that we can plot to help us understand how force is changing with extension. So we plotted force on the y-axis and extension on the x-axis, which left us with the gradient being the spring constant. And you can see that the gradient never changes up to this point here. So the gradient is constant. It's the same steepness up to that point, which tells us that the spring constant is a constant because the gradient is constant. How do we know that the spring constant is the gradient? Well, if we have F equals KE and we fit it to our equation of a line, which is y equals mx, plus c we don't have. So y equals mx, we can see that we've plotted force on the y-axis, so they match. Extension on the x-axis, so they match. Spring constant, therefore, is the gradient, m. Okay, so to be able to work out the spring constant from a force extension graph, providing that it is an elastic deformation, we just need to find the gradient of the graph. But that only applies up to the limit of proportionality, the elastic limit. So there is a point in every single material where you've stretched it so far, you changed its shape so much that it's not going to go back to what it was. Okay, so let's say you keep pulling a elastic band, and you always do it and you always push it really, really far. Eventually, it's going to reach its elastic limit. When it reaches its elastic limit, that rubber band will never be the same. Okay, so past that elastic limit, we don't see this linear behavior anymore. So here we have a straight line, nice and neat straight line, everything's proportional. If force doubles, extension doubles, really good. However, past that point, we don't have that linear relationship anymore. We've got this curved line, which means that for even the littlest force, we get more extension. So it's inelastically deformed. Okay, so it's important to note that Hooke's law, F equals KE, only applies to this linear portion of the graph here, this straight line portion of the graph. After that, Hooke's law does not apply. Okay, so only if we have a straight line and a force extension graph does Hooke's law apply. Now we have elastic potential energy. So when we put force on a spring, we create work done. Okay, so work is done when a force is used to change the shape of something, change the motion of something. So work is being done every single day, all day long. You're doing work all day, right? You might be pulling a door, that's doing work because you're using a force to change the motion of something. That's doing work. And it's exactly what we do when we pull a spring apart, or if a mass were to pull the spring for us. So work is being done when a spring is deformed, okay, providing that it's elastically deformed. So if it does go back to its original shape, work is done. That work done is equal to this form of energy called elastic potential energy. So a person puts work in to the spring, and the spring converts that work into elastic potential energy. They're equal. Now, elastic potential energy is one of our 7 forms of energy. We have gravitational potential, we have thermal, we have light, we have kinetic, lots of different energies. This is just one of the types. Now, elastic potential energy can be found when we have anything that is stretched and is held there. Okay, so anything that is stretched and is held there. So a spring just lying on a table does not have elastic potential energy. Only when we stretch a spring and hold it there is elastic potential energy being stored. Okay, so it's important to remember that, as it's a very common exam question to ask. It might give you like 7 different scenarios, and you have to say in which one's elastic potential energy is being stored. And they try to catch you out by putting just a normal spring there to try and confuse you, but you have to remember that only if it's being stretched and held there is elastic potential energy being stored. So we have an equation for elastic potential energy. So on the left we have elastic potential energy, which is a big E with a subscript little e, so a little e kind of down below, equals to a half ke squared. Now K and E have exactly the same meaning as they do in Hooke's law. So K is just spring constant and E is just extension. But we need to remember to square the E first and then times it by K and then times it by half. So although they won't do this in the exam, you need to remember that there are brackets around this part here. Just like normal bod mass, you always do the indices first. Okay, and then we went on to talk about the required practical. So the required practical for Hooke's law is, it's not too complex, but it does require quite a lot of calculations. So the actual setup of the experiment looks like this here. You're going to have a clamp stand with 2 clamps. On one of the clamps, you're going to hang your spring that you're investigating and your slotted mass carrier, which is this thing here. You're also going to put a ruler to the left-hand side of it, making sure that the 0 matches up the top of the spring. The ruler is there so that we can measure the length at each addition of mass. So what we're changing in the experiment, our variables, are the mass added. So each time we're going to be adding a 100-gram mass on. What we're measuring is the length, the change in length. So we're going to add a mass on, measure the length, add a mass on, measure the length, and keep doing that until we get to 1 kilogram. Then we're going to take the lengths away from each other to find out how much it changed. Okay, now you'll notice that we have force here, but we're adding on masses here. Remember, mass and weight are 2 different things. Mass is just the value. So 100 grams, 200 grams, 300 grams. But to be able to do this experiment and plot it on a graph, we need to work out the force. So we need to know how to go from mass to force, where the force is the weight. So we have a 100-gram mass being added on. How do we get to weight? So if we add a 100-gram mass on, how can we convert that mass into weight? Put your answers on the chat. See if you can work out how we would change mass into weight, because it's vital for this experiment and lots of other areas in physics. So I'll give you just 30 seconds to have a think about that. Okay, loads of you are saying times by G, which is really good. I've put it on the screen here even. You just want to times your mass by G. If you don't know what G is 9.8 and it stands for the gravitational field strength. Okay, so gravitational field strength, which is 9.8. Make sure you use 9.8. Don't round to 10. They won't accept it. And don't kind of round to 9, don't do any of that, just do 9.8 every single time and you'll be fine. So yes, we times by 9.8, but before we do that, because we have a 100-gram mass, we need to convert to kilograms first. So this equation only works if our mass is in kilograms. Okay, so kilograms times our gravitational field strength gives us our force. Now that we have a force in newtons, we can plot it on the graph. So this time they've plotted a force on the x, an extension on the y. Don't worry if you see this in an exam. They do this a lot. You might have learned a graph one way, but in the exam, they flip the axis around. It's really annoying, but that's why I say that you have to check the axis before you dive into any sort of graph analysis. So if we were to approach this exam question in an exam, we would be checking the axis first. You can see that it's not using the same units, it's using millimeters. Usually we see it as meters, and the axis is switched. So be really careful for that. And it doesn't matter too much. It just means that the gradient is now 1 over k instead of k. So we can see elastic behavior being seen up to that point there, at which point it reaches the limit of proportionality and becomes permanently or inelastically deformed. Okay. So you can see that they've left it in millimeters here, absolutely fine to do so. However, if you feel more comfortable working with meters, that's also okay. But millimeters would be an appropriate scale to use for this experiment because it's not going to change by that much. It's not going to change by meters at a time, is it? So millimeters are really the most sensible one to use. Okay, and then we moved on to displacement and distance, speed and velocity, and the difference between the two. So distance is just how far the object moves. It's one value with no direction, 3 meters, 3 miles, 5 yards, anything like that. We don't know what direction it's moving in. It's a scalar. Okay, so when it has no direction, it's a scalar. Displacement, however, is how far the object moves with the direction. So it's a vector. So if it's with direction, it's a vector. If it's without, it's a scalar. Same for speed and velocity. Speed is just a value of how fast we're moving. Velocity is how fast we're moving and where, in what direction. Then we talked about 2 different types of speed that we can have. We can have an average speed, which is the speed of an object measured over the entire journey, or we can have the instantaneous speed, which is the speed of an object at a specific instant. So an average speed would be the speed that you most commonly kind of do, average speed between point A and point B, over a certain distance, over a certain time. Instantaneous speed is what speed cameras do. They check your speed at 1 instant. They don't take into account the 3 seconds before that, 3 seconds after that. They only take that 1 instant. What speed are you doing at the exact instant that camera takes a picture? Okay, so the speed instantaneously. Then you need to know these common speeds, so walking, running, cycling, and sound, because we need to be able to compare speeds to these speeds. So speeds that you get in your answer, they might say, how does this compare to the speed of walking? And you might say that it's 4 times the speed of walking, half the speed of walking, whatever. So we need to actually remember these. You might want to remember it because running is walking doubled and cycling is running doubled. Okay, so that's how some people like to remember it. Then we move on to speed, distance, time equations. So S equals VT. And we talked about how this equation is quite annoying because of the letters that it uses. So S equals VT is confusing because S, you think, oh, S stands for speed, S is speed. Then you come to V and you think, well, what's V? Well, V is actually velocity. So S is not speed anymore, S is distance. Okay, S is distance. S is distance because S is displacement. So we needed a new letter for displacement, and so we thought we'd use an S. Don't ask me why, but that's what we did. We used an S for displacement and a V for velocity. So you can see that this incorporates the vector versions of each quantity. So distance or displacement, speed or velocity, and time is just time. Then we went on to talk about the higher tier idea, which is circular motion. So you only need to know this if you are higher tier. And it basically says that if an object moves in a circle constantly, so for an example, a car on a roundabout. So a car on a roundabout might stay with a certain speed. So let's say it does 10 meters per second all the way around the roundabout. Okay, so the car does 10 meters per second all the way around the roundabout. The speed never changes. That value never changes. Speed. But velocity, remember, incorporates direction. Now, the direction of a car on a roundabout is constantly changing. It needs to go left, 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 all the way around the roundabout. Okay, so the car's direction is constantly changing. It's going that way, that way, that way, that way, that way. So because the direction constantly changes, the velocity constantly changes, but it stays the same speed. A bit of an abstract idea, but velocity does change, speed doesn't change, which is why scalars and vectors are so important. Then we went on to talk about distance time graphs and velocity time graphs. So distance always plotted on the y, time always plotted on the x, velocity on the y, time on the x. So I just want you to tell me, what does a straight line mean on a distance time graph? So what does this line represent here, this purple line here? What does that represent? Have a think. So what does a straight line on a distance time graph represent? Put your answers in the chat. If you've done that, what does a flat line represent? So what does a straight slanted line represent, and what does a flat line represent? Okay, so a straight slanted line is a constant speed. So well done if you said that. And a straight flat line is stationary. So a straight slanted line is a constant speed. It does a certain distance in a certain time, and the gradient never changes. A straight flat line means that it doesn't go any distance in a certain amount of time. So time is going on, goes from 11 o'clock to 12 o'clock, but in that time they don't do any distance, which is why it's at rest. A curved line on a distance time graph is a special one. So a curved time means a changing speed. It's a changing gradient, so a changing speed. For a velocity time graph, a straight flat line means a constant speed. So it can get very confusing, which means we need to double check what graph we're working with. Because a straight slanted line on a distance time graph means a constant speed, but a straight flat line on a velocity time graph also means a constant speed. So the purple line here means the same thing as this red flat line here. A straight slanted line is a constant acceleration. The gradient represents acceleration, and the area under the graph also has significance. So the area under the graph is distance, is displacement. How do we find speed from a distance time graph when we have a curved line? So on a distance time graph, a curved line is changing speed. So how do we find that instantaneous speed in this portion here? So you can see that we've got a curved line, but in this region from here to here is pretty much a straight slanted line, right? It curves a bit at the ends, fair enough, but it is pretty much a straight line. So we're going to estimate it using a straight line. So we draw a tangent, which is this estimation by drawing a straight line that touches the curve at a single point. Okay, so this is our estimation, which is called a tangent. So it's a straight line that we draw which hits the line. Okay, now to find the gradient, we find the gradient of the tangent. So we do our change in y divided by our change in x, and we get a value. So you remember, you cannot find the gradient of a curved line. It won't work. You first need to draw a tangent and then find the gradient of the tangent. Okay. So we had two equations that we introduced you to with acceleration. So acceleration is the change in speed divided by time, or v squared minus u squared equals 2as, where v is the final velocity, u is the initial velocity, a is the acceleration, and s is the displacement. We also said that if the object is falling on this Earth, on this planet only, it falls with an acceleration of 9.8 meters per second squared. Always. Doesn't matter how heavy it is. Okay. So, two equations that you can use to work out acceleration, depending on what information you've been given in the question. So if you've only been given two speeds and a time, you need to work out acceleration using this equation. If you've been given a displacement and a final velocity and an initial velocity, you use this equation. So it depends really if you're given a time or if you're given a distance. And then we went on to talk about Newton's first law of motion. So Newton's first law of motion says that an object at rest remains at rest unless we hit it with an unbalanced force. The same with an object in motion will continue with constant speed and direction unless acted on by an unbalanced force. So an object at rest stays at rest unless we kick it. Unless we put some kind of force onto that ball, it stays there. It's the same with anything. You put your paper on the table, you put your pen on the table, it stays there unless you move it. That's all Newton's law is saying. The same with a ball flying through the air. So let's say the object is in motion. It continues with constant velocity unless it's hit by an unbalanced force. So, for example, a ball flying through the air ideally stays in constant motion. So Newton's law says that a ball carries on forever, moving in motion. But obviously, in real life, we know that's not true. Balls always come back down to the floor at some point. That's because of the unbalanced force, which is gravity. So gravity acts on it. It might be hit by a goal. It might be hit by another player's foot. They are all examples of forces which take that object out of motion. But if that force were never to act on it, it would stay in motion forever. So we have this idea called a resultant force, which is the unbalanced force. So when we put a resultant force on it, it accelerates in the same direction as that resultant force. Okay, so that's the first kind of third of the content. So if you do have any questions, please put them on the chat. I'll go through the Q&As now quickly. In what units extension or compression is measured? So extension and compression are measured in meters because it's just a distance. It's how far we've compressed it, how far we've extended it. I think that's all of them. So yeah, do you remember that Hooke's law can be used for compression or extension? Okay, I think that's all the questions so far. Just a note to say that I really try and put as many questions on the chat as you can. This is a webinar that is designed for you guys to kind of ask questions and flatten out any kind of misconceptions that you have. So no question is a stupid question. Do put it on the chat. You can even message me privately if you don't want to put it on the chat. But now is your time if you've been confused about any of the forces. Okay, so moving on to the next part of the content, we went on to Newton's second law of motion, which says that acceleration is proportional to force and inversely proportional to mass, which is all related with this equation F equals ma, where F stands for force, m stands for mass, a stands for acceleration. Mass of an object never changes. The mass of an object never changes. Okay, not at GCSE level. The mass is constant. Okay, so in real life, the mass hardly ever changes. So force, we can say, is proportional to acceleration. So if force doubles, acceleration doubles, remember that's what proportionality means. And then for force and mass, so acceleration and mass, if one changes, the other changes with 1 over it. So acceleration doubles, mass halves. Okay. And then we went on to talk about inertial mass. So inertial mass is again a higher tier concept, and it just says that this mass here is called inertial mass. So if your foundation is just mass, if you're higher tier, you need to know it that it can be inertial mass. So inertial mass is defined as the ratio of force over acceleration, and qualitatively, it's defined as how difficult it is to change the velocity of an object. Okay, and it might sound kind of obvious that an object with a greater mass is obviously going to be much harder to accelerate. It's much harder to push and change the speed of. But it's all because of this idea of inertia. So if an object has a greater mass, it has a greater inertia. And therefore, we need a greater force to cause the same acceleration as an object with a smaller mass. So let's take, for example, a car and a ball. So the car obviously has a much greater mass than the ball. So because the car has a greater mass, it has a greater inertia. And therefore, we need to use a greater force to cause the same acceleration as a ball. Okay, so if we want the ball to accelerate 3 meters per second squared and the car to accelerate 3 meters per second squared, we need to push the car much harder than we need to push the ball because of this idea of inertia. Then we went on to talk about Newton's third law of motion. So whenever two objects interact, the forces they exert on each other are equal and opposite. So we only think about one force. You've only thought about one force up to now, which is you pushing something. But we never think about the thing pushing back on you. So when you touch an object, when you touch a wall, for example, in the left most example, yes, you put a force onto the wall, but the wall also puts a force back onto the finger. Now, your finger doesn't go through the wall because the forces are equal. The force going in and the force to your finger are equal. Again, with a swimmer's foot on the wall, the swimmer pushes off, but the wall also pushes off. Skateboard pushes forward, but the skateboard also pushes backwards. Anything sitting on a table has a weight, right? We know that. Anything has a weight. Any object has a weight. The weight acts onto the table, so it pushes down on the table. But you also need to remember that the table pushes up on the object with a reaction force. So whenever we have two objects in contact, the forces that they exert on each other are equal and opposite. Then we talked about stopping distance. So stopping distance is made up of two distances, braking distance and thinking distance. So thinking distance is this idea that it's the distance travelled during the time that the driver takes to react. So as the driver is thinking about stopping, reacting to stopping, going to put his foot onto the pedal, that's all thinking distance. The driver is thinking about what his move should be. But the distance, the braking distance, is the distance that is actually travelled whilst the brakes are being hit. Okay, so two very different distances that work together to create the final total stopping distance. Now, the greater the speed of the vehicle, the greater the stopping distance, which is why it can be so dangerous to do high speeds, because it's so slow to stop. So we need to know typical stopping distances for an average car in normal condition. So in this graph, you can see that the thinking distances are in red and the braking distances are in blue. So if our speed doubles, so it goes from 20 to 40, if our speed doubles, our braking distance times is by 4. Okay, so we need to know these speeds, these thinking distances and these braking distances for every single speed. It's just a case of learning it. Reaction time is a factor that affects thinking distance. So if a driver has a bad reaction time, that's going to make the thinking distance much longer. And then what can reaction time be affected by? It can be affected by tiredness, drugs, alcohol, and other such distractions such as phones. How can we measure reaction time? Well, it's using the method which involves dropping a ruler between someone's open thumb and forefinger. So we have our ruler and you have person B dropping the ruler into person A's hand. So the person B is going to drop it, person A is going to catch it. Wherever person A catches it is how far it is dropped before they caught it. So if it's a short distance, they have a good reaction time. If it's a long distance, they have a very bad reaction time. Longer reaction times increase thinking distance. So what affects braking distance then? Well, braking distance can be affected by road and weather conditions. So if the road is really bad condition or it's icy, wet or windy, that can affect braking distance. Also the condition of the brakes and tyres. So if you haven't got your brakes checked or your tyres checked, that can affect braking very badly. What happens then with the forces and the work to when we apply brakes? So when a force is applied to the brakes, there is work done by friction between the brakes and the wheel. So remember, work done is when a force causes motion. So for us, the force is you applying the brakes and the motion is slowing down the car, which is done by friction between the wheels and the brakes and the wheels and the road. This friction reduces kinetic energy and slows it down, which in turn makes the brake's temperature increase. So it takes the kinetic energy out, so it reduces the kinetic energy, but then it has to store that kinetic energy somewhere. Remember, energy can't be destroyed, it can only be changed into a different energy. So the kinetic energy that we've drawn out to make the car slow down is put into the temperature of the brakes. So it's changed into thermal energy. The faster a vehicle travels, the greater the braking force needed to stop it in a certain distance. But a greater braking force produces a higher deceleration. But large decelerations cause the brakes to overheat and the driver to lose control. So they are bad. We don't want to produce great braking forces. Okay, so that's the second third of the content, and now the last third of the content will take you through what we've just done, pressure, and a little bit of motion to go. So we talked about the require practical. I won't go into it in too much detail now because it is quite a lengthy method, but if you do want to have a look, then it's in the motion and moments webinar. But it's basically investigating how varying the mass, keeping the mass constant, changing the force, keeping the force constant, and then measuring acceleration helps us to understand Newton's second law. And it gives out these two laws here, these two rules. Then we talked about moment. So moment is the turning effect of a force. So if we put a force to turn something, for example, in a spanner, a merry-go-round, a seesaw, or a door, so they all create a moment. It's a force that rotates something. So moment equals force times distance. That's the equation that we use for the moment of that force. Remember, distance is not just any old distance. Distance is the perpendicular distance from the pivot to the line of action of the force. Okay, so the perpendicular distance to the force here, the force acts downwards of the go. Perpendicular distance is that one because they're at right angles to each other. Okay, so it's easier to use a longer spanner when trying to turn a nut and easiest to push furthest from the hinge when opening a door. So that's why the doors are furthest away, the handles are furthest away from the hinge. Okay, it makes sense because having it further away increases the perpendicular distance to the pivot. If we increase the distance, we increase the moment. Okay, so if we increase force or distance, that increases the moment. A bigger moment means that it's easier for a human to move. Bigger moments are good for people. Small moments are bad. It's harder to push. We have to put more force in to create the same distance. Then we talked about the law of moments. You don't need to know how to do calculations with the law of moments, but you do need to know the qualitative, wordy kind of law. So if an object is in balance, for example, this seesaw here, the total clockwise moment, so the moment that acts on the right, equals the moment that acts on the left. So the force times the distance on the right is a force times the distance on the left. But we need to say, we need to call it in terms of clockwise and anti-clockwise. Because if you imagine the force here, if you imagine tying a string to it and pulling that string, that's going to cause the seesaw to go clockwise. Same for this, if you were to attach a bit of string to this force, pull it, it's going to cause it to go anti-clockwise. Okay, so we think about moments, not in terms of left and right, in terms of clockwise and anti-clockwise. And then we went on to talk about levers and gears. So levers consist of three different parts: a pivot, an effort, and a load. The way that the pivot and the effort and the load are arranged gives us different applications of levers. So if we have effort, pivot, load, it's a seesaw, crowbar, or scissors. Pivot, load, effort, wheelbarrow or nutcracker. Pivot, effort, load, tweezers or cooking tongs. So you can see how the examples in each section are quite similar to each other. Then we went on to talk about gears and how they work. So if we have two gears next to each other in contact with each other, the teeth both move in the same direction. So the teeth of the gears, the spikes, are both moving upwards and outwards. But the gears rotate in opposite directions. The forces acting on the teeth are identical to each other, but the moments are different because of the distance. If a larger gear is driven by a smaller gear, the large gear will rotate slowly, but will have a greater moment. Conversely, if a smaller gear is driven by a larger gear, the larger gear will rotate quickly, but will have a smaller moment. So just something that kind of needs to be memorized, one of those laws. Then we talked about pressure. So pressure equals F over A. Force normal to the surface over the area of that surface. So for an example, we used shoes. So a big kind of area of the sole of a shoe means that we have a reduced pressure. So if we have a larger area, we have reduced the pressure. Okay, larger area means a reduced pressure, so opposite to each other. If we have a large area, that reduces the pressure, which is much better for our feet in kind of snow or just daily life when you're wearing shoes all day, which is why high heels can hurt. So high heels they concentrate the force in a very small area. You have a small kind of sole at the front and then a heel at the back, which is obviously a very, very small area, which increases the pressure that we feel in our feet. Now that is usually for solids, and where we're not given the height, we're not given the density of the liquid. When we therefore move to liquids, remembering that a fluid can be a liquid or a gas, we move to pressure equals the height times the density times G, otherwise seen as P equals H. Rho, which is the Greek letter for density, kind of looks like a P, and then G. So that's a similar equation if you wanted to learn it like that. There would not be a triangle for this equation because there's too many elements in the equation. So if you do normally learn your equations and triangles, this is one of them that you won't be able to do in a triangle. But you will be given this equation, so don't worry too much. Now, we need to know for higher tier that pressure varies with depth. So the deeper the water is, the higher the pressure is. So at the bottom of the bucket, we go very deep, and therefore the pressure is higher than at the top of the bucket. The reason for this is that because at the bottom, it's got all of the water on top of it, weighing it down and putting more pressure on it. Okay, that's what causes the pressure. At the top of the bucket, it's got no water on top of it. It's got no pressure, no weight on top of it to cause pressure, which is why the pressure at the top is much smaller than the pressure at the bottom. Lastly, we went on to talk about upthrust, which is this idea that because an object partly or completely submerged in water experiences a greater pressure on its bottom surface than its top surface, we get a resultant force upwards. So it's forcing the object upwards. This is called upthrust. If the upthrust is less than the weight, the object sinks. If the upthrust is larger than the weight, the object floats. You need to know those two rules. Atmospheric pressure then is just this idea that we have a pressure in our Earth, which is caused by air molecules colliding with surfaces and with each other, creating this atmospheric pressure. Now, the atmosphere gets less dense as we get higher and higher from sea level. So the atmosphere is much less dense than at sea level. This is because the number of air molecules decreases as we get higher and higher. If the number of air molecules decrease, the number of collisions also decrease. If the number of collisions decrease, we're not creating as much pressure. So collisions cause pressure. You also need to know these two values, which is the pressure at sea level and the pressure at a cruising altitude, which is the average height that a plane normally flies at. Okay, so exam technique. What are my kind of top tips for you guys taking exams? Doesn't just apply for the formal GCSE. Any physics exam that you do, these are some great top tips. So, bullet points for long answer questions. It's absolutely okay for you to write in bullet points. It can really help to structure your answers, and it's not important to write kind of in an essay style with posh kind of connectives. No need for any of that. bullet points will suffice, and it can help to really split up your ideas into concise kind of ideas. Next point is to sense check your answers. So sense checking is this idea of kind of using your real life conceptions to help you sense check your answers. So let's say you're working out the speed of like a really, really fast runner. Okay, so you're going to go back to your speeds that you've learned and know that, okay, the speed of a runner is roughly 3 meters per second. Really fast runner, okay, they might get up to 5 meters per second. And that is what we call sense checking. So if you're getting an answer out that is like 200 meters per second, you know that's wrong, right? So always sense check your answers. Think, actually, is that sensible? Is that a sensible value for what I'm trying to work out? If it's a really fast runner, it's not going to be 200 meters per second, okay? Always write with basic, easy to understand answers. Nobody cares about posh language, posh definitions, posh adjectives, nothing like that. Just easy, straight to the point answers. The examiners will be happy because they don't have to read waffle, and you'll be happy because you don't have to write that much. When you're doing calculations then, always check the units in the question. So remember the standard units that we work with: meters, kilograms, seconds. Meters, kilograms, and seconds. If you've got anything else apart from those three, change it. So unless the question asks for you to put your answer in millimeters per minute, change it before you do any calculation. Because trying to change at the end is going to be super hard. Write down the equation that you intend to use, whether it's from the equation sheet, still write it down, or from your own head, because you do have to learn some equations, write it down. The examiner then knows that even if you got the calculation wrong, your intentions were in the right place. You intended to use the correct equation. Then rearrange the equation for whatever you're trying to work out, and then substitute your values in. For graphing and graph questions, check what is on the axis. So, for example, earlier we saw that force and extension were flipped. That can happen. Check the units of the axis, they can switch it up. When finding the gradient on a graph, so for a distance time graph or a velocity time graph, make sure you use a big triangle. So don't draw a tiny little triangle in one section of the graph. You will not get the marks. You want to use as big of a triangle as you can to get the gradient. Don't use it, be specific. So when I say this, I mean that let's say the question asks, what is the motion of the car after it passes the traffic light, for example, okay? It speeds up and then it slows down. No, we want to say the car speeds up, the car speeds down. The person experiments with this, the student does this. Never use it, because when there's more than one component, so this is very appropriate in practicals, we want to be really specific because there's lots of different things going on in a practical. Use diagrams if possible, especially for forces. For moments, make sure you get the perpendicular distance. They will try to catch you out by using maybe 3 different distances. You need to pick out which one the perpendicular one is, so the perpendicular to the force. Perpendicular just means at right angles to. Be specific with vector and scalar quantities. If the question asks you to talk about the velocity of the car, make sure you don't just talk about the speed. Talk about the speed and the direction. Okay, if the question asks you to talk about velocity, it's not going to be enough for you to just talk about speed. Don't overthink required practicals. They sound scary because it's required and it's practicals and it's lab work and it's a specific method. The method does not need to be word for word. Schools do require practicals in very different ways. The required practical methods that I've given you are the ones that I think are the easiest to learn, but there can be lots of different methods for the same experiment. So make sure you know one and then know how to explain it. But remember, the method does not need to be word for word what I've told you. As long as you get the gist of it and the correct physical ideas, it will be fine. The most important thing in required practicals is not the method, it's the graph and the analysis. Your results table, what you're going to put on the graph. They don't really care if you kind of mess up the method a bit, if you put maybe step 1 and step 2 in the wrong order, most of the time it won't matter anyway. Okay, so in the setup on the required practical, let's say you put the air track down first, then you put the mass on top, or you put the light gates first, then you put the mass carrier on. That does not matter. Okay, so don't stress about them too much. Although you have done them in school and you have been given a method, it does not need to be word for word. And finally, get the correct Newton's law. Some people tend to mix them up and think that they all kind of merge into one. They're very specific and very individual and apply to very, very different scenarios. So make sure that if a question asks you to give your answer with reference to Newton's law, make sure you know which one you're going to be talking about. That is all of my top tips for a physics exam. The ones at the bottom are obviously more specific to forces, and the ones at the top are just general things that you need to know. That's all I've got to say. I think there's a few questions. So what age year is this for? This is mostly year 11, but the speed, distance, time stuff is year 10. What exam board questions did we do today? Well, we didn't do any questions per se, but everything that I kind of do is taken from the AQA exam board. So I base all my webinars on the AQA exam board. The questions are from there that we do in webinars. But there is quite a lot of overlap between the exam boards. Can you choose which exam board you would like to do for GCSE? No, if you are in a private school, grammar school, any type of school, you can't choose. The school chooses for you. However, if you are homeschooled, you can choose. Can you explain the equation F equals ma again, please, especially what the force is? So F equals ma. Force equals mass times acceleration. So the force required to accelerate an object equals the mass of that object times the acceleration. Okay, so the force that we push, so let's say we're pushing a ball to accelerate it, we push it, that force equals the mass of the ball times the acceleration of the ball. How many marks will calculating the elastic potential energy be in a synergy AQA exam? I would say it's probably going to be 3 marks. So 1 mark for either correct rearrangement of the equation or the kind of squaring of the E and getting everything in the right place, getting the right information for each of the quantities, timesing it all together, then getting the right answer. So most likely going to be 3. Sometimes they might do significant figures, so give it to a certain amount of significant figures, that's going to be another mark. Newton's first law of motion is that if an object is at rest, it tends to stay at rest unless it's acted on by an unbalanced force. If an object is in motion, it stays in motion unless it's acted on by an unbalanced force.
Cool, I think we'll end there right on time. Thanks for all those questions today. And I think that was a really useful session. I think exam techniques are so valuable. So thank you very much, Preshayla. And guys, just a reminder that these sessions are always recorded. You can access them on the My Tutor YouTube channel. And if you're joining us for any other sessions today, we've got English coming up in 15 minutes, and then maths at 2, and a history session at 3:15. If not, if you only join us for physics, then the next session will be next week. So we'll see you then. But thank you very much for today and have a great afternoon, everyone. Bye.
Bye.